Hey, thank you all for attending the U.S. Former Force Association webinar series. And this is a webinar number 10. The topic is Unified Facilities Criteria Foundations for Structures, Arctic and Subarctic Construction. My name is Musial. I'm a faculty member at Penn State and the past president of the USPA. And the USPA webinar series is sponsored by Arctic Foundation's P&D engineers, Shannon and Wilson and WSP. We thank the sponsors for supporting USPA, and their sponsorship goes to the travel fellowship or award for USP members. And the format of the webinar today is we're gonna have about 45 minutes talk, and from the seven presenters themselves to introduce, and then we leave about 10 minutes and for Q&A. So I'll leave the rest to Dr. John Thornley to coordinate. Thank you.
All right, thanks, Ming, and yeah, looking forward to this presentation. And we'll start off by Kevin Bjella introducing the panelists for today's discussion. So thanks, Kevin.
All right, hello everybody. Thank you for joining us today. We're glad to report on this this big project that we've been working on for the last 4.5 years or so. And so the folks that are these are some of the participants that participated in the revision of the UFC. It was a very large project. There's quite a few more that participated, but these are some of the main players and that we're able to present today. So myself, I was the lead on the project with Dr. Rosa Affleck. She was a great co-lead. She's senior researcher at Hanover and CRREL. CRREL and Hanover. I'm with CRREL at Fort Wainwright in Fairbanks. Dr. Wendy Wieder also was a great support on this project and co-author. She'll be presenting. Mark Musial with WSP. John Thornley and Andrew Daggett were great contributors for Volume 3, which is the foundations volume out of this 5-volume set. And then Dr. Wade Lein, who's a senior researcher at our Hanover CRREL office. And he participated with the buildings volume. So next slide, please. So in a nutshell, there was a lot of reasons to revise this document. But just in a nutshell, this is a Department of Defense, UFCs are Department of Defense engineering guidance documents that are wide-ranging, from pavements to painting to building materials, runway lighting, just about anything that you can think of when it comes to DoD infrastructure. And way back when, in the 1950s and 60s, the Army had technical training manuals for constructing in the Arctic and Subarctic. And those were agglomerated into the UFC Arctic and Subarctic Construction, a 7-volume set that, so that was put together in the 80s. But none of those technical manuals were revised when that was all put together in the 80s. So really, we've been looking at this Arctic and Subarctic Construction Design Guide woefully out of date, since one volume in particular, the pavements volume, was 1957, I believe. And so we were having a major issue. USACE was having a major issue with Arctic construction, and our clients questioning how we were coming to our specifications and our designs when we were actually relying on guidance that was that far out of date. And so we partnered with ESTCP, CERTUP ESTCP, which is primarily a DoD funding agency, and they provided the money to redo this. This is a little bit out of the sequence of how Tri-Service updates UFCs, but they funded this entirely, and it was a great project. You can see those that are that were involved on this screen here. Quite a few. And we have a technical report that we put together for CRREL, and it lists everybody specifically. And if you take a look at that document, you'll see that there were quite a few people that provided their expertise for this. So next slide, please. Yeah, so that I kind of briefly talked about the motivation, but here were the original 7 volumes. General site provision, site selection and development, runway and road design, foundations and structures, utilities, calculation methods, and buildings. We reorganized this a little bit. The first big diversion here is that runway and road design was pulled out of this because AFCEC is actually redoing the temperate region UFC for runway and pavement design, and putting a cold regions amendment to it. So that was already being done, but otherwise we took all these other topics and we reorganized. We folded calculation methods for depth of freeze and thaw into volume 1, and Rosa will talk a little bit about that. Site selection, that's the volume that I revised, and that's still about basically the way it was. Volume 3 is foundations. WSP will talk about that. Volume 4 is buildings. Wade Lead, and we'll talk about that. And utilities was Wendy Wieder. And next slide, please. And applicability, I'm going to turn this over to WSP to let them tell you from the industry point of view their standpoint on this. Thanks.
I think this one's mine, Kevin. It's Mark Musial. I'm in our office with Andrew Daggett. I have to apologize. We're having video problems here. They may even start while we're in the middle of talking about this slide. We'll see. But so one of the first questions, with any code is what's it applicable to, and what regions is this applicable to? And so from as everybody here in the USPA knows, there's multiple definitions of what sort of Arctic or subarctic, and how do we define them? Is it circumpolar? There's many different terms for it, and ERDC and CRREL arrived at this general definition of applicability. It's northern areas. The Arctic's northern areas. Generally, it's permafrost areas, but not always. And then it goes down into the subarctic areas, which arrived at basically north of 50 degrees. Which is pretty fair, but I think it also applies to places like the Aleutians, high altitude, mountainous permafrost. There's all the stuff in Tibet and southern Siberia. Anyway, it's applicable to a lot of areas, and another place is there's elements that we talk about in this criteria that are just applicable to cold regions in general, and that's areas of deep seasonal frost. And so there's concepts and ideas that are included in this that are relevant, even though they aren't strictly applicable. I guess I'll turn it over, John. You want to advance?
No, thanks, Mark. I think one of the key pieces to understand and take away from the UFCs is they draw a lot on the International Building Code. And so when you look at UFC in general, it cites back to the building code where it makes sense, and then where there are special considerations, the UFCs take those on, whether it be a special facility or something that's unique to DoD works. And the goal of the UFCs for the cold regions work that we're discussing is to draw on the IBC, but also show some of the differences and some of the challenges that a typical design engineer may not be thinking about if they get a project, say at Fort Wainwright or Eielson, or somewhere where there's deep-seated permafrost or deep seasonal frost. And one of the other goals is to provide references for engineers to really understand and dig into cold regions engineering practice. So we weren't trying to develop a series of manuals that are explicitly design guides, if you will, but provide references and information that engineers practicing in cold regions would be able to draw on to dig further into as they're working through design or planning and design. You know, as we said before, the focus is on Arctic and subarctic issues, but what we've seen in the past, in just Alaska in general, not necessarily focused on DoD facilities, is poor performance and failure, expensive mistakes where potentially a temperate region engineering has cost you know, a lot to essentially repair and upgrade to deal with unique conditions in cold regions. And then, you know, increased maintenance cost due to these utilizing practices from temperate regions that may not fit very well within this. And so the document does cite a number of standards and organizations such as ASCE and ASHRAE and others, but then tries to provide that cold regions twist, if you will, on what you know, what to be considering as a you know, a design engineer potentially practicing in another state may not be thinking about when they have a project in Arctic and subarctic regions. And another kind of interesting piece is that last bullet, this introduction to risk assessment, reliability, and resilience. There's not a lot of guidance out there, and so what we wanted to do was draw on the resources that were available to then pinpoint and provide direction for projects and engineering design that attempts to work through that risk assessment, reliability, and resilient aspect, because those are important and critical aspects to DoD projects. And so with that, I will turn the mic over to Rosa.
Alrighty. All right. As Kevin alluded to, we now have these 5 volumes, and these are the new names for these volumes. And we've listed the corresponding lead author for each of this. So the UFC 3-13001 is now titled Arctic and Subarctic Engineering. This one serves as an introduction to the Arctic Subarctic UFC series, and I led the revision to this volume. But there were a lot of contributors to this for sure. The UFC Volume 2 is now titled Arctic and Subarctic Site Assessment and Selection. This volume provides technical guidance for all about technical site assessment, and Kevin is the lead author on that, and he'll talk more about that in the next few slides. Volume 3 is titled now Arctic and Subarctic Foundation for Freezing and Thawing Conditions. This applies, this guidance applies to horizontal and vertical foundations, as well as consideration affecting foundation designs and construction, and also listing, highlighting monitoring of facilities there too. This was done again with our colleagues from WSP, which is great to have them helping us out through the contract with Alaska District, and did a lot of technical review to other volumes. Alaska District is really helpful in a lot of these revisions. Volume 4 is titled Arctic and Subarctic Buildings. This applies to everything about building designs, such as building envelope, snow loads, and roofing, etc. So this was initially written by my colleague Lynette Barna, and then Wade took it over after Lynette retired. So Wade will talk a little bit more about the overview of that buildings in the next few slides as well. And lastly, the Volume 5 is Arctic and Subarctic Utilities. This applies to criteria and guidance for everything utilities, including water, wastewater, utilidors, electrical and communication, and Wendy was really instrumental as the pioneer of doing this revision. And so with that, I'm going to hand you over to Wendy.
Good morning, good afternoon. So Tri-Service, or the Army, Air Force, and Navy, administer the UFC program, and it's a big effort. They have multiple discipline working groups that fall under the standard engineering disciplines, and those people sponsor these documents. For R3, they were sponsored by the civil, the architecture, and the geotechnical groups. These groups are 3 to 5 members, and they have a review authority, and then they sign off, and then it goes up the chain to the level of the Office of the Secretary of Defense. Once these are all reviewed, and this is a multiple month, perhaps even year process to get through the whole program. It is available, the final documents, on the Whole Building Design Guide platform, and the criteria management program itself is required a login and is basically all, as I said, the surface people. And then I'll turn this back to whoever is next. Sorry.
So, as John alluded to about the content of the UFC, Volume 1, the new Volume 1, lists the standard practice used in the temperate region because it's part of the format that Tri-Service, as Wendy alluded to, we have a format that we need to follow when we do our revision. So we basically have to enumerate the temperate UFC, but more importantly, I want to highlight that we really highlight a lot of the classical cold regions infrastructure problems that have several causes to infrastructure, such as settlement due to thawing foundation, effects of frost action or on frost heaves, the influence of salinity on frozen soil properties, the implication of foundation engineering, earthwork, and other aspects of construction. So this volume also includes a lot about cold regions engineering, design, and construction in locations that have extreme low temperature. So those extreme zones with freezing and thawing, also those other fluctuations on the other side, snow and ice, frozen soils, and many other cold regions, environmental and ground consideration. We've included the implication of changing climate. That's for sure, it's happening in the Arctic. This volume also includes current guidance and approaches on snow drifting or wind-induced snow movement, ice load, icing, ice cover, ice on water bodies, ice engineering, snow hydrology, and its distribution on snow, snow melt, and drainage and groundwater. Like it was highlighted in the beginning, we've included risk and resilience consideration, not only because you have to deal with the harsh condition, but as well as the inherent issues related to the changing future, changing the climate trends. On this slide, you could see some examples that we've put in this volume to look at design freezing index using current data. And so we've really tried to incorporate a lot of new materials on the volume. And that's what I have for Volume 1. Over to Kevin.
Okay, thanks, Rosa. So I revised Volume 2. This actually started with a previous project that I had with CERTA, looking at better ways to characterize permafrost, better methods and assessment techniques. And so something that CRREL has been doing for quite some time, for decades now, is working with surface-based geophysical methods, radar, resistivity, those types of things. And so that was a big part of what I brought to this volume. This volume was very much out of date with its, I think it was called Site Selection before, and that utilized mostly photogrammetry, photo analysis and photogrammetry techniques. I don't even think it talked about terrain analysis. It predated some of the terrain analysis methods that were devised for the pipeline. So it was woefully out of date. So it was time to bring this into the 21st century. And basically what I did was take a look from the 30,000 foot level, basically the desktop level, down to subsurface, where you would actually be perhaps drilling a hole or doing some soil sampling. That was the methodology that I utilized. And of course, a big part of that is that we believe is part of that characterization should be geophysical techniques. So next slide, please. So we go through quite a detailed assessment of what can be done and how to get from that 30,000 foot level down to that sub-centimeter or centimeter level at the subsurface, depending on what type of project it is. Is it a vertical construction project? Is it a linear infrastructure project? What type of materials are you going to be investigating? Because that has implications on drilling techniques and the drilling tools that you might have available. So this volume goes greatly into depth of how to go from that desktop assessment, pre-field visit, all the way down to actually putting soil in a bag or in a core, and then getting engineering properties from it. And I think I'll just hold that there. If anybody has any questions, please ask at the end of the seminar, but I'll pass it on to WSP now. Thank you.
Hello, this is Andrew Daggett. So once we have the information that we collected in the volume 2, we need to then move into the design stage, which in this one, since we're covering Arctic and subarctic areas, we have a wide range that we need to cover. First, we're going to cover our standard foundation design for freezing and thawing conditions, where you're going to have a frost protected foundation. And then in addition to that, with our Arctic conditions, we have to worry about permafrost. So we have, how are you going to design a foundation in permafrost to keep everything frozen? So with that, we're trying to, this manual provides a broad overview of several topics which would be important in the design of the foundation. So first, it would be how you're going to use climate. What's the best way to use the new changing climate information? What should we be looking at? And then with that, what does that mean for our ground temperature regime? Are we going to be seeing a significant change in ground temperatures that we need to consider in our foundation design? So a little bit on the numerical modeling. And once we've kind of have an idea of what the climate and the ground conditions are going to do, we touch on the actual foundation design pieces, what should be looked at for vertical and horizontal structures. And then we have sections on drainage, and then performance monitoring and maintenance. Next slide. Then Mark is going to kind of discuss this one.
All right, thanks, Andrew. So what you have here is a flow chart, basically, that outlines how the volume is organized. Now, it starts up with the high-level issues of any site, because this is designed for both permanent facilities and temporary facilities, like with that expeditionary forces, I'll say. So, it's taking a look at some of the high level items that have to be thought about. It goes back into the site investigations, and you get into this sort of loop thing about how the site investigations are informed by geotechnical engineering concepts and thermal analysis and design issues. And that all comes down then again to some preliminary foundation engineering. It wraps around looking at alternatives and whatnot. Maybe you'll need to do some additional investigation for a real significant facility. Maybe you really don't need to do anything for someplace where you're going to be for a month in the wintertime. But it just is intended to show how there's this thought process that people can follow along. It goes down then into the final foundation engineering and cost and functional analysis, might wrap back again into final design, and then construction, performance, and maintenance. And each of the chapters that those items are discussed are in there. Now, when we first started this thing, we were supposed to have like under 40 pages of text or under 50 pages of text. And this volume quickly grew into a large volume. And we had to bring this outline together because we engaged a lot of people from the engineering community through ASCE Cold Regions Engineering Division called CRREL. And as you can imagine, if you take a group of engineers and scientists and throw them on a conference call, they all have an idea about what should be talked about and what order things should be discussed. And so we sat down with that and we tried to distill it into these major items and organize a volume around that. I'll pass it on to the next slide, John.
Hello, everyone. The next volume in this series is the buildings volume. And this volume, we worked with the architectural discipline working group. And so it has specific considerations for architectural, structural, mechanical, fire protection. And really what we looked at in these sections were, common pitfalls and things to consider when you're designing in a cold region. And things like, in the architectural volume, they're looking at the building envelope or architectural section, the building envelope, and, what kind of doors to use and things like that. The mechanical one, you're looking at HVAC systems and things like that. The electrical one, you're looking at things like, make sure you're putting outlets outside for vehicles, if they need to stay warm. Fire protection, that one's pretty self-explanatory. You want to design your fire protection systems to work in the cold, so you don't want ice coming down on your exterior outlets and inlets, and then you also you want them protected as well, so that they don't freeze up. Things like that. There's different materials considerations. You can see one of the examples here for different types of materials and making sure they're compatible with cold regions. And then roofs, you want to design your roof in such a way that you limit and minimize snow accumulation and ice accumulation. All of those are things that we wanted to talk about in the buildings volume. And after that, I'll pass it off to Wendy with the utilities volume.
So for the utilities volume, this goes back, the material that was in the original volume, to a 1970s conference that was held in Canada. And it was a symposium on utilities delivery in the Arctic regions. That large volume of work that was in that symposium went to the EPA and then went to ASCE and the Army and produced documents such as the Cold Regions Utility Monograph from ASCE. And then it produced the technical manual that was the predecessor to this UFC. So it was some information from the 1970s. It considered all utility systems. And what we did in the case of the new volumes is separated it into thing that was hard criteria and best practice. And then we could use material that came out of, for example, Canada, where they use some best practices that aren't actually code per se. But this document does refer often to the ASCE Cold Regions Utility Monograph, or CRREL, which is also currently under revision, and it does introduce and look at a wide variety of utility systems, from laying it on the top of the ground to putting it into Utildor. Next slide, please. And then we did take an opportunity, after talking with several different people, to step back and actually provide some of the basics that may be now in computer models, but just to make sure everyone knows what we're going for, especially, as we say, sometimes in the government, a Florida design firm might get a new control tower for somewhere in the Arctic, and they don't know. And that's what we want them to know. We want them to know that they don't know, so they can come and consult with someone who understands and can help them through these issues that may be a significant problem to the utility system. And I'll turn that back now.
Okay. Well, thanks everybody for highlighting your sections there. I do have to apologize to everyone. There was a side project to this funding that we received, and that was to create kind of a living guidance on permafrost temperature evaluation. So we had a contract with the Geophysical Institute Permafrost Laboratory up at University of Alaska Fairbanks, um, and Sergei Marchenko was providing his input on ground temperature modeling, something that they had been doing for quite some time. They had a portion of Alaska uh, codified utilizing existing borehole temperatures and then applying those to an average of 5 climate scenarios with different RCPs, one RCP of 4.5 and an RCP of 8.5. And this allowed them with different surface treatments, whether it's natural ground or gravel or even insulation added to a gravel pad, to be able to project permafrost temperature out to 100 years. So we paid Sergey to create this for the whole state of Alaska. Um, and unfortunately, Sergey passed away last year, as many of you might be aware. He was able to complete this project, and we transitioned that particular aspect, that tool, over to Scott Rupp and his team over at SNAP, the Scenarios Network for Arctic Planning, and they incorporated it into their new Arctic EDS database and website. Many of you might be aware of this, but if you go onto that site and you look under a particular community or coordinate location for Alaska, and if the permafrost information is available, you'll be able to tap into scenarios that have been run under different surface treatments, and then project the permafrost temperature at various depths out to 100 years. So we felt like this was very important because engineers across the spectrum, whether the academia, industry, or government, are kind of figuring out their own way to assess risk due to the rising climate, the rising climate, rising temperature, and the changing climate. And so this was one way of actually trying to bring that down to a codified method. So this is something that will always be updated based on the revision of the 3 averaged climate scenarios. And so we believe that it's a good way to move forward with forecasting permafrost temperatures, which for permafrost engineers, we know that that is so important for how we design and the level of effort that we put into the foundation elements and so forth. So unfortunately, I should have had a slide for that, but I did not include that, and I apologize. Please, you can send me an email and ask for more information on that if you're interested. But in conclusion, we just wanted to let everybody be aware that this has been completed. There's a lot of information in here. The format required that we cut it down from the original. So those of you that are familiar with the old UFC will see that a lot of the material has been culled out, especially when it comes to case studies. That's how a lot of the cold regions guidance and engineering really was collected and published in previous years, was because there wasn't a lot of strict guidance like you would find for, say, electrical systems or plumbing systems and so forth. There was a lot of reliance on case studies. Here's what I did and here's how it worked, or here's what I did and here's how it perhaps failed. So a lot of that's been removed, and it is more per their format of actually providing links to other standards and so forth. So you'll see that there's quite a change, but there's a lot of good information in there. And with that, we also realized that we missed some things. We probably actually missed a lot of things, even though this was a 4-year effort, and we really tried to get in there everything that we could. The UFCs are really good about allowing users, stakeholders, to put comments in, get into the criteria management system, and log in what they call CCRs, criteria change requests. And so if you're going through a volume and you see that something is wrong, something is misspelled, there's a typo, whatever it might be, or we totally missed and you need to get something in there, please go into the whole building design guide, get into the criteria change request for that particular volume, and enter in that note. These are, I believe, are scheduled on a rotation basis of 7 to 10 years or something like that. That money will then be applied to do a revision. However, that is based on comments. That's based on CCRs. And so if a volume has a tremendous amount of CCRs, then it will come up for review much sooner. And so, if there's something that we just absolutely missed and it's absolutely needs to get in there, then that can kind of be forced to make happen on sooner. So anyway, the bottom line is that everybody has the opportunity to make comments on this and get them in there so that this is basically living documents that can be revised. And that will be revised. So with that, thank you all to all the presenters, and thank you all to those who joined in today. And here's some of the list of the folks that helped us. Again, we have a technical report, a CRREL special report actually, and it goes into a great deal of the folks that helped. I really want to make a shout out to the Alaska District. They were substantial help on this. They are a major stakeholder as one of the USACE districts that does cold regions engineering. And so John Rajic, Jim Sacita, Amy Steiner, Doug Bliss, they were all very instrumental in helping us work contracts to get experts on board and then provide their expertise because they do a lot of Arctic construction. And so we wanted to make sure that we got the blessing from them before anything went through publication. But you'll see a whole list of other folks there that are probably familiar to you if you've been working in cold regions engineering for some time. And so, a great shout out to everybody that helped us with this. Everybody was very enthusiastic and wonderful to work with. So I think with that, I will stop and please, we're here to answer some questions. It looks like we still have quite a few minutes left. So thank you again.
All right. Thanks, Kevin. Thanks, everybody here. So I'm going to go ahead and read off some of the questions for the group, and we'll see what answers we can provide. So the first one is for the Arctic and subarctic site assessment and selection. What do you think about the role of remote sensing technologies in this process? Are there any particular promising remote sensing methods or data types that are well suited for cold regions? I'll give that to you, Kevin.
Yeah, absolutely. That is part of the process, starting at that, I said 30,000 foot level. I should probably have said, the 60,000 or 100,000 foot level if we're talking about space-based remote sensing. But absolutely that plays in. Remote imagery, that's probably the first one. When you're really looking at picking out features, especially with permafrost terrain, just looking at straight imagery is wonderful. Some of the SAR imagery is very useful. Some of the L-band stuff. I'm not a particular expert on remote sensing from space and how that's applied to the permafrost terrain, so I don't want to muddle this up. But definitely that is in there. It's part of the very beginning. It's part of the desktop survey methods to then move from the desktop to the field. So yeah, absolutely.
All right. The next question is from Jeff Curry. Hi, Jeff. The question is, does the UFC 3-13003 address frost design for intermittently heated and just barely heated structures? Seems like frost protection would be pretty complicated when the floor/foundation heat flux is highly variable. So I'll pass that over to Mark.
Does it address that question? I'll say no, not explicitly. The UFCs are written to provide general guidance and allow engineers to do what engineers should be doing, which is thinking about the problem and applying appropriate solutions to that can be vetted by others and reviewed and understood. So I think it's a great question, but we don't. These documents don't have real explicit guidance on how to do something. It points you to the direction of what's maybe been published today, and again, it reinforces why it's a living document. Things are going to be changing. People will be publishing new things, and it still gives the engineers a lot of flexibility on how you address a specific problem. I hope that helps.
Great. Thanks. Let's see. Next question from Thomas Bergelin. Hi, Thomas. The American Society of Civil Engineers, during their ASCE 722 revisions, was asked about how they were accounting for climate change. Their response was that ASCE deals with historical climate data and does not use projections. And so, in effect, ASCE 722 does not account for climate change in its minimum design loads and other structures. In light of this, how does the UFC justify using climate projection? And I think that kind of follows in on some thoughts that you were sharing, Kevin. I don't know if you want to take first whack at this.
Well, we didn't specifically address that, as a contrary to what we were doing. I think negating that there's climate changes would be woefully inadequate. We all know that the permafrost or the air temperature is changing, and consequently, the permafrost temperature is changing, which affects the strength of the ice matrix and any ice features that are in the ground. Overall, the permafrost strength, and then that affects very seriously how you design your foundation. So, if this is contrary to what ASCE has specified, that's unfortunate. But really, what we wanted to make sure that there was some way that engineers could say that they were working collaboratively with one method. If they want to venture off and do their own method for calculating risk for the rising air temperature and then rising permafrost temperature, they can certainly do that. But for those that were wondering what would be a best method to do it and something that actually is living and using current climate scenarios, that's what we felt was the most important to include. So certainly if there's somebody on the panel that would love to add to this, please do.
And I'll throw it over to Mark and Andrew as well. I think there's some elements in the foundation guide.
Can I add on that, John?
Sure.
All right. So ASCE 7, when we talk with our snow load experts, actually, we wanted to make sure that we incorporate some of those changes. But what he guided us is that ASCE 7 will keep changing. So we should be just putting it to say ASCE 7 without indicating whether it's 22 or 16 or what have you, because they'll probably be changing over the years, and UFC will be changing a little bit on the off scale. So ASCE is a living document. It changes every 12 years versus ASCE 7 probably will be changing every 5 years. So that's the reason why, as going back to Kevin's point, is that we wanted to make sure that there's flexibility in there and not to provide really concrete documentation and which one to follow. But just to add to what Mark was saying is just to make sure that engineers should be thinking along those lines of some of those risks in the changing climate for design loads, because it's not incorporated. And how do we incorporate that? Perhaps you do some sort of looking at what that condition would be like in, say, 10 years, 20 years, 50 years, whatever your design for the facility is. So that's what basically how we went about referencing ASCE 7 specifically. So I hope that answered that question. I'll let Mark and those others add to that. Thanks.
Thanks, Rosa. Yeah, and so in volume 3, we do address climate and environment. Right, there's many elements there to consider, and there is recognition in there. I think there's some examples that are included in the UFCs about different approaches that people may take with that, and recognition that there's a warming environment out there in the north, especially. So it is discussed. It provides general guidance, though, as a factor that needs to be considered. I don't think we come out explicit to support one method or another, but it references things like SNAP. It references the global climate models that you know, some people might choose to look at all of them and make some judgment as to what's appropriate for any given site condition. But it is certainly addressed in there. That's all I had, John.
Great. No, thanks. And then just to follow up from Thomas, we're already considering this, but you're codifying how we should be approaching this. And I think people may have different opinions about that, and whether that's being codified or if you know, these are things that allow you to do good engineering in the Arctic and subarctic. Any other comments?
It's criteria really that we provide, and we point people to approaches, right? It's not necessarily codified, though.
Right. Otherwise, there wouldn't be a section on numerical modeling, because you wouldn't necessarily need to model anything and choose, you know, what the structure may behave like in the future. So, any other questions? These are great, questions, comments. We've got a few more minutes here, so happy to take any more that you might have.
Well, and in the meantime, thank you, John. And if any of our panelists has any insight that you think might be helpful or informative for our participants, and you can share that as well.
Well, I would add that UFC revision is really unique. It is not like writing a technical manual or report or technical report. It's a totally different format. So as an engineer, a researcher, it was difficult for us to break away from the construction of the sentences is totally different. So just kind of how we showed some examples of how it was written, that's how it was. And then there's that we have to consolidate that into maybe a paragraph. So it's really tricky. So that's what I have to say about revising a UFC.
So we have a question from Eric Williams. What is the importance of live data in monitoring sites? And I'll take maybe a whack at that initially. I would say that I'm going to assume that we're talking about monitoring sites that are the part of the built environment, and so I think you could break it up into two main categories. One would be, you know, sites where we're anticipating imminent failure, like if we're monitoring a retaining wall that's moving. The live data then, you know, helps you understand you know, when failure is imminent. But I would say that live data with monitoring sites over time gives you a trend and an understanding. In the thermal environment, things don't happen just overnight, right? We see these trends in time that hopefully we can rectify when we reach a certain threshold or trigger, if you will. And so, while maybe one individual piece of live data is not critical for, say, long-term monitoring, it does allow you to understand trends in behaviors. And so I'll turn it over to others in the panel if you want to take on the importance of live data, or Eric, if I've missed your kind of the gist here, let us know too. But Kevin?
Yeah, I'll chime in here. So the project that kind of led to this 10 years ago, the CERTA project that we had for permafrost characterization, one aspect of that was what we termed as early warning detection. What kind of new tools are out there? If you've got structures, linear, vertical, that are on frozen ground, what kind of sensor technology could be utilized to give somebody a heads up? And so we titled that early warning detection. It's pretty fancy because really the only thing it boils down to is temperature monitoring. I mean, there could be some some ground movement that you could utilize depending on what the structure is, but really it's temperature monitoring. And a lot of the work that I do, I'm on a lot of new design project teams for Arctic infrastructure for DoD across North America and Greenland. And so we try to incorporate this quote unquote early warning detection as much as we can, because another portion of my work is trying to assess what's happening with degrading permafrost under a structure that might not have been adequately designed, or that structure has been altered in the past and now it's affecting the foundation stability. And so the one thing that always comes to mind if you're trying to assess a structure that may be experiencing permafrost degradation is it permafrost or is it something else? Is it possibly frost heaving? Is it perhaps vibrational loads from equipment that might be in there? Is it just perhaps design failure? The foundation was not adequate. So that very first question of answering, is it permafrost? The only way you can answer that is with permafrost temperature. And so we have finally gotten it pretty much into the vernacular for any new infrastructure across the North for DoD, that there must be some level of permafrost monitoring. And ideally, it gets tapped into the building DADC so that it can be just constantly monitored. The beautiful part about that is then if you can actually get it to an alarm condition. So if you have a temperature string at various temperature strings at various points under a structure, and you identify which sensors, if they get to a certain temperature, then they would alarm. And this allows people to look back and say, well, here's how it's changed since the building was constructed, and whether actually permafrost thaw is part of the problem. So yeah, I would say it's incredibly important, and trying to get that into the client's budget to actually get that into the structures is in my opinion, just it's as important as a good solid foundation design.
All right, we've got another question here from Bear Jiang. This is a follow-up and general question about remote sensing. What are the most promising INSAR applications in Arctic and subarctic environments? Could you share some examples, example use cases? Anybody on the panel want to take on the INSAR applications question? No, Kevin, that's part of your work.
Yeah. So yeah, this is an interesting one. I have seen a lot of presentations and a lot of people that have very successfully used INSAR. We have terrestrial LiDAR at our laboratory that our technicians have tried to be able to utilize and get the same results that that I've seen in presentation. One particularly striking presentation that I saw was for Yellowknife Runway, and it showed centimeter scale deformation over time right at the junction of the main runway and the crosswind runway. And I know it exists there because I've been there, and I know that deformation exists. However, it's very time consuming. It's computationally intensive to try to get that differential measurement, but I know it works. I've seen it. I've seen people do it. Our lab just has not put a lot of time into it to make it work. So I think it's incredibly valuable. If there's somebody else on the panel here that can add to this, I would say yes, INSAR is an up and coming, really good technology.
Anybody else on the panel want to?
I agree. It has a place. It's often a cost benefit decision. And from an engineering perspective, anyway, you have to inform your clients of what those benefits might be, and make them recognize that it's not just a summer-long project. It might be a multi-year project that you're going to have to buy into. We do use it in the far north, and I think it again has benefits. Looking at things, there's also some downsides of it that people might get expectations that can't be met really by the technology, and the technology is constantly improving though too. So I'm supportive of it in general.
Great, thanks.
Can I say one last thing about code?
Sure.
So we drove all the temperate engineers crazy because in many cases, and my understanding, there is no code for some of the things that are done in Arctic and subarctic engineering. So the UFCs are written with requirements, guidance, commentary, and best practice. So we don't necessarily we're not necessarily putting into code some things. We're providing the guidance and the best practice as to how that is working in the Arctic and the subarctic now. And that did drive some people crazy on tri-service because they just have no experience up there. This is the group of people who have the experience up there, and they just didn't know how to handle that. So we had to look very carefully. As Rosa mentioned, we had strict guidelines, the use of the word must, things like that. We had to tiptoe around some things a little bit, but it was our intent to provide an engineer, a practicing engineer, with the guidance to do things correctly, not be prescriptive, but give them the guidance to get a good product. And that's what these UFCs, that's the intent. Thank you.
All right, looks like we have time for one last question. Bill Brooks, hi Bill. For monitoring, are you seeing distributed fiber sensing used to monitor permafrost temperatures, say along buried utilities? And I know CRREL has been looking at this. Maybe Kevin, I don't know if you want to take a first stab at this.
Yeah. So we've done a lot of DAS, well, DTS, I said, distributed temperature sensing. In fact, we have a makeup, a faux embankment 500 feet long. It's a typical roadway section built on very ice-rich permafrost. It's got ACE embankment, ACE shoulder treatment, and we've got 2 levels of DTS layered through it. And this is wonderful. The really nice thing about the DTS is that the cable itself is really cheap, in perspective. Now the acquisition equipment is not so cheap. That's kind of the more difficult part of it. But the cable anyway is very cheap. And so putting that in just to have something that you could go back and look at if there are problems in the future, just like I said earlier about having that early temperature warning, a baseline, is so important. But yeah, we're starting to see this now. As far as utilities, I have advocated for this on a couple projects that I've been on. One was in particular in the natural gas line for coming down from Prudhoe Bay. That should be part of the codification on that, at least a requirement. But whether we'll see that actually be a requirement, I'm not sure. But yeah, I think distributed temperature sensing is a wave of the future.
And Dr. Zhao, I know you could have another webinar just on that topic alone as well, but I'll turn it back to you, and I think our time is up.
Thank you all so much for this very informative webinar. And so that concludes our webinar. Thank you all. And I'll follow up with the email to the participants with the PDF version of the PowerPoint. Okay, great. Thank you.
Thank you.
Thank you, everybody.